for fish and wildlife that are unique to Hawaii and that rely on fresh water during some part of their life cycle. And so now I'd like to describe some of the changes in groundwater quality and quantity that indicate that management is needed to maintain the conditions and to protect the public trust resources that I just described. So I'm going to talk about rainfall across the aquifer system and salinity and nutrient data from observation wells within the park and on the boundary, the northern boundary of the park, and also data, water level and salinity data from pumping wells inland of the park and to the south of the park. So Kona is currently experiencing severe to extreme drought, and although drought is short-term, in Kona it's frequent and severe relative to the rest of the state. And University of Hawaii researchers have determined that the Kona area has experienced the largest long-term declines in rainfall in the state. And so preserving freshwater flows is a natural defense against these changes. And within the park, we monitor salinity at 3 observation wells using continuous transducers. And we also recently started monitoring salinity in a piezometer in Aimakupa Fish Pond. So these transducers measure specific conductance, and the salinity, or the specific conductance of seawater is about 53 millisiemens per centimeter. Okay, so the wells with the longest record are Kaho 2 and 3. The red line is Kaho 2, and the blue line is Kaho 3. And there is a long-term declining trend in salinity in these wells. And water quality data indicate that salinity is declining because irrigation water from the golf course is flowing into the park. So I want to be very clear that we do not consider this impact to be a benefit to water resources in the park, because the irrigation return flows are high in nutrients such as nitrate. And nutrients can cause harmful algal blooms, eutrophication, and they can shift reef communities dominated by corals to algal-dominated systems. So Honoka'a Harbor is listed as impaired for nutrients under the Clean Water Act, and the nutrients are from treated wastewater effluent. And this chart shows nutrients or dissolved nitrogen in the alkaline pools and in the wells in the park. And statistically significant increasing trend in nitrogen and phosphorus was observed in alkaline pools in the park, and nutrients are increasing in Kaho 2. And reducing freshwater flows to the park will increase the concentration and residence time of these contaminants in the park's waters. So before I advance the slide, I just want to point out a nutrient spike in 2009, and this was in the alkaline pools in the northern part of the park. And this nutrient spike was also detected by the USGS in MW401, which is a well on the boundary between the park and the golf course. And this nutrient spike, or this chart is from the report. It shows that nitrogen, dissolved nitrogen, was many times higher than background levels in this well in 2009. And the USGS concluded that these nutrient loading at MW401 was due to fertilizer. So MW401 is a relatively deep well. It's about 100 feet below sea level. And it was constructed as part of the permit conditions for the pumping wells that provide irrigation water to the golf course. And the golf course collects monthly salinity profiles in the well. And I extracted the minimum and maximum specific conductance from those profiles. And the maximum values suggest that salinity is increasing in this well. The minimum values suggest that salinity is decreasing. If you look at the values that were collected after a new logger was used, it suggests that both the minimum and maximum values are increasing. And chlorides are also measured monthly in this well. The chloride data has a lot more variance in it because the sampling methodology is not as precise. But these values suggest that there is no trend in salinity. So the data are difficult to interpret. And after discussions with Waimea Water Services and the USGS, I think that two continuous fixed, continuous transducers in this well would provide us with more useful information. And I think what we can learn is that if we're going to use monitoring data to protect public trust resources, the data need to be reliable, actionable, and there need to be management triggers associated with the data.
Could you tell us about the transducers? I mean, it seems like it's a big different profile after they were changed, and what's the difference between those and what you're calling for?
Oh, these salinity profiles are collected with a transducer, and it's put in the well and then lowered and kept at a certain elevation for maybe 5 minutes, and then lowered to the next interval and left there. And then so you do one profile in 1 day, and what I'm suggesting is that instead of doing that, you take 2 transducers and fix them at a certain depth in the well, and then you would get continuous data over time at those 2 elevations. And I think the variance would be much less if you look at the fixed transducers in the wells in the park. They provide pretty good data with much less variance. Does that answer your question?
Sorry, just a question. Roy, do we have fixed transducers? And I can't even say the word this morning. I'm sorry, I didn't have any coffee. Excuse me. No. Okay.
Okay. So I'm not implying the golf course is complying fully with their permit conditions. So I'm not implying that they're not. Just that there's something we can learn from the data that we've collected to this point. Okay, so that was data from observation wells, and now I'd like to discuss data from pumping wells and why we're seeing adverse impacts at pumping rates, even though pumpage is below the sustainable yield. So the Commission staff have determined that water levels in the inland aquifer have been steadily declining since 1991. And the Hualalai Deep Well, this is water levels in the Hualalai Deep Well, which is directly upgradient of the park. And the pumping rate in the well is less than 1 million gallons per day, and the pumping rate in the aquifer system is about 50 million gallons per day, and sustainable yield is 38 million gallons per day. So water levels, this long-term water level decline is occurring even though pumpage within the aquifer system is well below the sustainable yield. And these are chloride data from the Kahaluu well field, which is about 8 miles south of the park. And chlorides are increasing in these wells even though the pumpage is well below the sustainable yield. And this is chloride data from the Kahaluu shaft again, with pumpage data from that well. And so saltwater intrusion is occurring in this well, and chlorides are exceeding the recommended level for drinking water at pumping rates well below the sustainable yield. And Commission staff have determined that this pumping is unsustainable. And so these are adverse impacts, and they're occurring even while pumpage is well below the sustainable yield. So if limiting pumpage to the sustainable yield cannot prevent saltwater intrusion in a coastal pumping well, then how well will limiting pumpage to the sustainable yield, how well will that protect coastal public trust resources? I think that this idea that as long as pumpage is below the sustainable yield, that there are no problems and no adverse impacts, that this has been the biggest obstacle to collaborating around a solution to the issues that we've raised. So I'm going to talk briefly about why we see adverse effects at pumping levels below the sustainable yield.
Excuse me, a quick question. Doesn't that really have to deal with the actual location of the well? I mean, we know the lower elevation wells have high level salinity and the plans are slowly to move up to the higher level, doesn't that really have a big impact on that last?
Exactly. Okay, so sustainable yield is calculated using this equation. It's the Robust Analytical Model, or RAM, and it treats the aquifer system as a reservoir, so that recharge raises water levels the same amount everywhere, and pumpage reduces discharge to the coast by the same amount everywhere. And so this model ensures that pumpage never exceeds the rate of recharge, or the average rate of recharge. But it does not tell us what level of development is sustainable for any individual well or public trust resource. And that's because the model depends on recharge. And there is a common misconception that as long as pumping is less than the rate of recharge, that the development is sustainable. But the idea that recharge is important at all in determining the level of sustainable development is a myth, and it's called the water budget myth. And the reasons why are clearly explained by C.B. Tice in 1940, but since then hydrologists have found that it needs repeating. And this misconception has great consequences for ecosystems and other water users, because in truth all water withdrawn by wells must be balanced by a loss of water somewhere. So to protect public trust resources, we need to ask not what is recharge, but where are the losses, and are they acceptable? So for example, let's consider a gaining stream prior to development. The stream could be any kind of recharge boundary, like a stream, or like the ocean, or a fish pond, or an anchor-line pool, or a tide pool. If we pump a well next to the stream, initially all the water withdrawn by the well is removed from aquifer storage. And reducing or removing water from storage in an aquifer, the impacts of that are declining water levels, and if the well is in a freshwater lens system, it's rising salt water. And now these impacts can affect nesting habitat for water birds in a nearby wetland, or water levels in a nearby well, or cause upconing in the well itself. And the well will continue to remove water from storage until the area affected by the well intercepts the stream or the coastal pool or pond. And then the well starts to capture groundwater that would otherwise discharge to that stream or pool or pond. And the impacts of capturing freshwater discharge are stream flow depletion and a reduction in freshwater discharge to the coast and saltwater intrusion. And so now the well could impact habitat for stream-dwelling damselflies, anchor-line pool shrimp, habitat for culturally important fish, and lemur growth along the coast. And so the amount of water captured by the well is equal to the withdrawal rate of the well. So capture occurs at pumping rates well below the rate of recharge. And this is why everywhere that I work, South Dakota, Oklahoma, Nevada, Utah, and Hawaii, we see water disputes at pumping rates well below the rate of recharge, because all of the water has to come from somewhere, and either aquifer storage or captured discharge. And so all pumping has consequences and is only sustainable to the degree that we are willing to impact public trust resources and protected water rights. And so the challenge is identifying where the capture of fresh water is going to occur, and what level of impact is acceptable.